In the next couple of videos, we're going to investigate what happens when we throw a horizontal shrink into our trigonometric equations. For our first example, we'll try one without a horizontal shrink in it. We'll just say solve the sine of theta is equal to root 3 over 2. Now, because we have something involving a sine, and because it is a positive value, that means that we would be looking for a total of 2 angles. Those 2 angles would be the 2 angles from the unit circle, where we would observe a y-coordinate of root 3 over 2. Or, with that in mind, if we wanted to consider the function y equals the sine of x, which looks approximately like this, across its first period, and we wanted to consider where y is equal to root 3 over 2, we'd be looking for the 2 points of intersection that we find within that first period. So one here and one here. A decent working knowledge of the unit circle will let us know that the 2 angles that we're looking for within that first period are pi over 3 and 2 pi over 3. Now, if we wanted to do this a little bit more generally and say that this is true for any angle, or outside of just the first full revolution of the unit circle, then we could also express it in the following fashion. We could say theta is equal to pi over 3 plus 2k pi, or 2 pi over 3 plus 2k pi. So this recognizes that the 2 angles within the first full revolution of the unit circle are not the only solutions, but rather anything coterminal to those angles created by rotating a whole bunch of times would also technically work. Or if we wanted to consider what's going on with the sine function, we are saying for all intents and purposes that if we look for those points of intersection through all real numbers, we're going to have 2 points of intersection per period. So 2 in the first period, 2 in the second period, 2 in the third period. Now, what each of these actually represents is a number of full rotations that has actually occurred up until this point. So, for example, between 0 and 2 pi would be considered k is equal to 0. Between 2 pi and 4 pi would be considered k equals 1. Between 4 pi and 6 pi would be considered k equals 2. Now, generally, we look for solutions that are within 0 to 2 pi. However, as soon as we throw in a horizontal shrink, or what I call in class frequency modulation, all of a sudden, 0 to 2 pi contains a lot more periods than just what we're used to seeing. For example, if I gave you something like the sine of 3 theta is equal to root 3 over 2, the significance of that 3 is that now, between 0 and 2 pi, you can fit a total of 3 periods. Yuck. That is not a great drawing, but it's okay. We'll make it work. So once again, if we consider y is equal to the square root of 3 over 2, now there would be a total of 3 solutions that lie within 0 to 2 pi. Once again, the significance of all of these is each of these represents how many full periods have taken place so far. So with that in mind, here is the strategy that we're going to take for something like this. So first thing we'll do is solve the basic equation. And we'll give the general solution. Now, in the context of what we're doing with this problem, we'd be saying that 3 theta is equal to one of the 2 angles or one of the 2 general solutions that we saw earlier. So either pi over 3 plus 2k pi, or it's 2 pi over 3 plus 2k pi. Now, because of that extra multiplier in the form of 3, we're going to have to finish solving for the variable. regardless of that variable is theta or alpha or x or whatever. This can be accomplished by multiplying both sides of both equations by 1/3. What this will do for us is pi over 3 will get multiplied by 1/3. We get pi over 9. And 2k pi will be multiplied by 1/3 as well. We'll get 2k pi over 3. Or theta is equal to, once again, multiplied by 1/3. 2 pi over 3 becomes 2 pi over 9. And 2k pi becomes 2k pi over 3. Several values of k will produce an angle between 0 to 2 pi. In the case of this multiplier being 3, there are a total of 3 values. And in general, when you have the sign of b times theta, or b times x, then b equals 0, 1, 2, all the way up to k minus 1. Let's see if I said that right. No, I don't think I said that right. It'll be k is equal to 0, 1, 2, all the way up to b minus 1. There we go. That's the right way to say that. So overall, there are going to be a total of b values that actually work. So in the context of what we're doing here, because the multiplier is 3, there will be a total of 3 values of k that actually work. The 3 values of k will always start at 0 and go up 1 at a time. And as soon as you hit that next value, we're going to be outside of the interval 0 to 2 pi. So then what we'll do is we will plug in k equals 0, 1, 2, all the way up to b minus 1 to get values in the interval 0 to 2 pi. Now this is going to require a little extra work on the user's part because I'm just about out of page here. But for k equals 0, this one is relatively straightforward because the 2k pi over 3 terms, they'll both become 0, and we'll just get theta is equal to pi over 9 or 2 pi over 9. These correspond to the first 2 values that we see for k equals 0. If we do k is equal to 1, we'll get theta is equal to 2 pi over 9 plus 2 times 1 times pi over 3. So 2 pi over 3. Or theta is equal to pi over 9. Probably should have done that one first. Plus 2 pi over 3. Here's where the little extra work on your part is going to come in. Get a common denominator for both of these cases. This one over here, common denominator is 9. You'll wind up with 7 pi over 9. And for this one here, common denominator is 9. You'll get an 8 pi over 9. And finally, this is not going well. For k equals 2, we'll get theta is equal to either pi over 9 plus 2 times pi over 3, so 4 pi over 3, or 2 pi over 9 plus 4 pi over 3. These will produce, and once again, I'm going to rely on you to do a little bit of work here. Common denominator of 9, you'll get 13 pi over 9 and 14 pi over 9. These would correspond to the last 2 values in the k equals 2. The 7 pi over 9 and 8 pi over 9 would correspond to the 2 values here within k equals 1. I think we should probably do another example of this.